Welcome to Basic Filtration. Well, we start by breaking down the contaminants in water into groups so we can understand what we need to do to manage them. First, we start with solids, things you can see. This is the bits of debris, rocks, twigs, frogs, that type of stuff. It's in the water supply that we want to mechanically remove. And then there's things that we can't see. This is particulate that's so fine that it stays suspended, kind of like dust particles in the air. You can barely see them. Well, those are quite large. We're also talking about things potentially about the size of bacteria as well we want to remove from the water supply. These are things we cannot see. And then there's chemicals, things that are intentionally introduced, such as sanitizers and flocculants. We want to remove those things because those things impact product quality and taste and odor and equipment as well. And then the chemical byproducts of sanitation and other things in the water like pharmaceuticals and other organics that have taste and odor impact upon product. And then we have dissolved liquids and gases and solids, where we mainly focus on the dissolved solids portion of this. This is the overall mineral content of the water, and that we may need to adjust it or tweak this to get it to meet our application specifications. And solid contaminants. We measure solid contaminants by the general name of turbidity, the overall number of floating particles in the water stream. This can be dirt and sediment, colloidal particles such as silica or ferric iron, bits of wood pulp, anything that can be found in nature that can be ground up small enough to essentially float in water. And to give you some relative sizes of particulate in the water, you have a human hair is around 75 microns, and what's visible to the human eye is 40 microns. Well, cysts, bacterial cysts, the eggs of bacteria, go down to 1 to 4 microns in size, and a micron is 1/25,000th of an inch, so we're talking very, very small things here. Well, turbidity, if you notice in this pipe, this layer of sludge built up, that is the turbidity that's settled out in the pipe and possibly rust and corrosion to this cast iron pipe. But over time, that debris settles out. And in the spring, if you've ever seen them flush fire hydrants, this is the debris they're trying to remove. Just because it's settled out in the pipe doesn't mean water will not pick up this debris as it goes downstream. So the older the plumbing, the more debris and turbidity you're going to have in the water. That's independent of the water quality going into the pipe and how much turbidity it has. So solid contaminants, how do we get rid of them? Well, solids in the water are just like other things we're used to filtering, like a coffee filter, a kitchen colander or fishing net. These are things which we're straining the water out and getting rid of the water and keeping what's left behind. Well, in food service filtration, we're doing the same thing, except we're reversing that process and keeping the water and getting rid of the solids and particulates that we don't want in the water. Now, solid contaminants in quick change filters are going to range from a half micron, which is about here, and larger. And when we get up in the 5 to 10 micron range, we're really talking about particulate removal with pre-filtration. And below that, below 5 micron and below, we're kind of dealing with carbon filtration, not only to do chemical removal, but also potentially bacterial removal at half micron levels. Now, chemical contaminants, getting rid of them. Where do chemical contaminants come from? Well, chlorine and chloramine are intentionally introduced to systems to act as disinfectants. And the disinfectants are intentionally produced. Chlorine has byproducts called trihalomethanes that are potentially carcinogenic, and activated carbon will remove those as well. And as it goes through the treatment process, you have pre-chlorination and flocculation. And flocculation is normally assisted by chemicals like aluminum sulfate, which will precipitate out particulate as it moves downstream. Well, that's typically added in excess, more than what's needed to get as much of the debris out as possible after the settling tank. So some of that chemical gets pushed downstream, and where it makes it out to the final dispense point, picking up turbidity on the way and settling it out. But it will also help cause material to stick to the surface of your filtration equipment, and that aluminum doesn't stop working when it's in solution just because it's trapped on a filter. It's going to pick up particulates on the way, causing a fine filter to become even finer over time, leading to short filter life. Then there's pH adjustment, which can impact filtration when it's done to a high enough level. You normally see higher pHs and flocculation coincide because higher pH helps the flocculation process proceed. Chemicals that are accidentally introduced, you're talking about pollution, chlorine byproducts, volatile organic compounds in the case of like a chemical spill, or industrial and agricultural pollution runoff from roads, streets, human life in general. And then the age of the distribution system. You may have lead service plumbing out there that may be leaching small amounts of lead into the system. There may be dead legs in the system that may cause biofilm to break off and travel downstream. These are the most challenging issues. If you run into problems with this, please call Everpure Technical Support or your local regional ops manager to help you through and specify correct solutions for these particular problems. Well, chemical reduction is undertaken in food service applications for the most part via activated carbon, food-grade carbon, and it's manufactured from coconut shells, hardwoods, and coal. It is then fired and steam cleaned and quite often acid washed to remove impurities from it and activate the sites on the carbon that will do the chemical removal for us. And then it's ground to a specific mesh size, whether it's granular or powdered, according to a OEM specification or the application they wish that carbon for. When we handle TDS, there are three approaches to handling mineral content in water, and the first one is to remove TDS. And when we remove TDS, that has two approaches. That is reverse osmosis will remove TDS and drop that level completely to 90 to 95% rejection, and that allows us to then blend back mineral content and fine-tune water to specific applications. We can convert TDS. We can take the hardness and heavy metals out of water using a water softener, and then converting that or trading that or exchanging that for sodium, which is added into water in those metals' place. We can handle TDS by using scale inhibitors such as polyphosphates, which prevent calcium and magnesium from forming hard scales. They will also sequester mineral content into solution so that they don't precipitate out and form hard scales. And phosphates, when they do form a scale, tend to be a soft, mushy scale that is either easily flushed out or easily dissolved with deliming chemicals. The other way we handle TDS is alkalinity reduction. By using specialized softening techniques in Clarus products, we're able to not only reduce the hardness, but the alkalinity as well, and have some tools in the Clarus family to handle corrosion and and scale control at the same time. Those are typically low volume applications. Scale and corrosion control equal cost control from an equipment perspective and a product quality perspective. Now, how we convert TDS in the softening process. The heavier metals in the water will come in and push off sodium and bond to this resin bead, and the sodium is pushed downstream. And converting TDS is typically called softening. You may have also heard this called ion exchange because the ions, the +2 and larger metals, were exchanging for the +1 sodiums. And this is what happens in this type of water treatment. As you can see before and afters here, there's little or no difference in chlorine or TDS. You may actually see a slight increase in TDS due to the sodium being in the water. It conducts electricity a little bit better than the other dissolved ions, so that's the reason for the bump there. Hardness, though, is where you see the drop in greatly reduction. This will quite often be greatly reduced or even zero. Bicarbonates are not affected by water softeners, cation exchange water softeners, nor is the chloride. Handling TDS, phosphate. The phosphate prevents scale from forming and does nothing for corrosion at the levels at which we can feed it for food service. At high enough levels, phosphates inhibit corrosion, but at the levels that were appropriate for food service, it will not. But before and after, if you notice, there is no real change in the water chemistry. All we're doing is adding a chemical that sequesters calcium and keeps it in water, along with magnesium and iron and other +2 metals. And when it does form scale, it forms a phosphate scale, not a carbonate scale. And this scale is a soft, mushy scale that breaks apart and dissolves easily. Now, when we're talking about removing TDS, we're talking about using reverse osmosis, which essentially is a very fine mechanical filter like a calendar, but the holes are so tight that we're actually straining out molecules. So it's down to even ionic levels of mineral content like calcium and magnesium. And since pretty much all membranes in food service are thin food composite membranes, they all have a carbon filter in front of them to protect them, so you get a reduction in chlorine, a 90 to 95% reduction in TDS, an exact same proportional reduction in hardness and bicarbonates in the water, and chlorides as well. This is important for corrosion control because chlorides are the leading cause of corrosion in stainless steel and waters in the United States. And how reverse osmosis works, there's a restricted waistline that controls the reject rate of the water being forced in under pressure, which is then applied to the membrane. And essentially this membrane requires you to push the water through it because it's so tight it takes a driving force. And all that mineral content is left behind to flow out the waste tube. So as we go down this membrane and we reject more and more of the TDS, this becomes more and more concentrated in TDS as we go down the membrane. And then the water that comes through is going to have 90 to 95% less mineral content than this side, where it's sent out to a storage tank, such as a bladder tank, RO-Mate 40 or such here.